Recall that we've been playing a lot with integrals lately. We've been thinking about what integrals represent. We've been thinking about what the integral notation represents and adjustments we need to make to the integral notation to make it fit with what we're trying to do. And we talked about the structure. Oh, I think I already said structure of the notation. We got to talk about the structure of the notation. So what we're doing is setting up an expression over in this part. So in this case, it just says 1 dV. But in the past, we've used this to be, say, height times length, or height times area, or in the case of this triple integral down here, some height times a volume to get like a 4-dimensional volume. We're developing an expression over there of something that we want. What we're going to do is plug a bunch of values into that expression, then add up the results. That's the weird part to say it like that, because when we're integrating, we're adding from a continuum. So there's nowhere to put the plus signs. But fortunately, we have mechanics to get around that. We know that if we find the antiderivative and plug in the endpoints, that will tell us what the sum is of the continuum. So our job became, how do we describe the region that we're plugging in, or the interval that we're plugging in, or the solid that we're plugging into the expression, so that the integral understands what we're trying to tell it. So we've talked about 2 different coordinate systems for a plane, for R2. We talked about rectangular coordinates, and we talked about polar coordinates. In rectangular coordinates, both variables represent some kind of distance, length times width. So setting up dA was real simple. We just took dx times dy. Dx is a length, dy is a length, so dx dy, that's going to be an area. When we started describing the plane with 1 length and 1 angle, then we had to do some stuff. So d theta times dx is not going to give us an area, because d theta is not a length. The units of d theta are going to be in radians. That's not going to turn meters into square meters. So we took that d theta and asked, how far is this little rectangle from the origin? Because then we'll use arc length. So this extra factor of r comes from the arc length formula to turn d theta into a length. When r is very small, d theta is going to be very small. But as we get further away with the same angle at the origin, that d theta is going to become wider and wider. Once we have that extra factor of r in there, the d theta became a length multiplied by the dx is also a length. So I got an area. We got an area. You were there too. So that extra factor of r was from the arc length, since d theta is not a length on its own. We had to figure out how far we were from the origin, or sorry, the pole, to turn d theta into a length. At this point, we've kind of covered everything. If we want to measure R2 with lengths and angles, one of them has to be a length. Think about solving triangles. I can't ask you to solve a triangle by giving you 3 angles. I've just given you an uncountable infinity of triangles. They're all similar, but we can't nail it down to 1 triangle. So we don't have a coordinate system for R2 that consists of 2 different angles. Let's keep that we need 1 length in mind when we drop down to triple integrals. I know we haven't talked a lot about triple integrals, but the big idea behind the integral is that in these kinds of integrals, in these double and triple integrals, we've so far been able to set them up with what's x between, what's y between, and now for a triple integral, we just added on to that, what's z between. So now we're going to have a dv This is going to be some small rectangular solid from which we will evaluate a function of 3 variables to get a, I guess, 4-dimensional volume. Hard to picture now. But all we're doing is taking 3-dimensional space, x, y, and z, and we're taking a dx, a dy, and a dz to make this little box, this little rectangular box. That's going to be our dv. What's x between? What's y between? What's z between? Z is just going to be the height above a point xy. These are rectangular coordinates. Note that all we've done is take our normal Cartesian coordinates with an x and a y, and we've said height above the xy plane. We just took the xy plane and extended up through z. And z is the height above the xy plane. Also note that we have 2 ways of describing this xy plane on the floor. With x and y, well, I'm calling it the xy plane, but we also have polar coordinates. We could also describe the floor with polar coordinates and just say height above the floor in polar coordinates. I put dx over here. In my mind, after I was talking, I was like, oh, you haven't written dr. And I'm like, oh, shut up, mind, I'm trying to work. It's like, oh, dude, but you haven't, quiet, you. And then I'm like, just noticed. There's finally enough of a break. The message finally got through. This is not a dx, this is a dr. If I could just edit this in post, then I would just like edit it back and go back and Photoshop out the X and put in the dr. That would avoid having to like reshoot the whole scene. I have a feeling like, I don't know if you remember, there was like a coffee cup scene in Game of Thrones, and I think they probably digitally removed it by now. They probably knew after they shot the whole scene that the cup was there. And someone must have been like, oh man, we left the cup in there. Do we have to do it again? It's like, oh, no, we'll just delete it in post, make a note of that. And then someone said it out loud. It's like, oh, yeah, I'll take care of it. And then the episode went up. It's like, oh no, I just forgot something. Anyway, that's the way I picture it in my mind. They're like, oh, no, that was good. Let's just move on. Anyway. I want to do a whole movie like that where the actors aren't supposed to have coffee cups in their hand, but they're just shooting the scene, like standing there with coffee cups in their hands. Like, well, we'll just delete them later. Don't worry about it. And every once in a while, they'll be talking, and then they'll take a sip. And it's like, well, why did the actor just do that? Don't worry about it. And they'll be like, well, this looks weird. Anyway, what are we talking about? Oh, yes. So notice I just took that dx dy, how I'm describing the floor, and describe it and putting a z-axis on top of it. And we can do the same thing if we describe the floor with polar coordinates. But just like with polar coordinates in 2D, if I want a volume, I'm going to need an r d theta dr. Notice this is just describing the floor and sticking a height on top of that. Rectangular coordinates are called rectangular because the x, y, and z form a little rectangle. But here we've got an r, a theta, and a z. So instead of our graph paper, our 3D graph paper, looking like little boxes, our 3D graph paper is going to have cylinders because the different values of r form circles. So we call these cylindrical coordinates. Note that in cylindrical coordinates, we've got one angle and two distances. R and Z are distances. Theta is an angle. Since I'm doing this in the context of integration in a triple integral, and dv has to be a little box, I still need to turn my theta into a length. So I still need this extra factor of r. Notice that this fits with our polar coordinates. Cylindrical coordinates are just polar coordinates with a z-axis. Just like rectangular coordinates are rectangular coordinates with a z-axis. That's all we've done. Floor can be x and y, and then that's a z-axis. That corner over there is a z-axis. Or we can describe the floor with r and theta, and then we put a z-axis in that same corner. Any questions? The other thing that you want to see, rectangular coordinates, all three are distance. In cylindrical coordinates, 2 are distance, 1 is angle. Any questions? How's everybody okay? Playing structure today. We're just implanting structure today. Not worry about the mechanics, no trig substitution. Because there's a third for our triple integrals. You can see because I didn't go across this way where 2 would fit. You should have been suspicious when I'm like, oh, I wrote this one, then I wrote over here. It's like, whoa, 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 whoa. That's where the second one is supposed to go. And then I have to be like all Yoda's. No, there is another. In this case, there's a third one. That's what I was expecting the new trilogy to do. It's like, oh no, they're going to be run out of Luke and Leia. It's like, oh no, there's a third. And then they just introduce another L word person. L name. Larry Skywalker. They were triplets secretly. Ha! Because that's the kind of schlocky writing I expect from my Star Wars. I'm not saying I don't like it. I'm just saying it's kind of bad. That's all. Don't be insulted, Disney. Disney doesn't understand like good writing versus bad writing. Because as far as they don't care about good writing versus bad writing. They only care about one thing. More money versus more money. Why spend the money to write a good story when you could just animate it into a profitable story? You know what I mean? Like they made a live action Lion King. Everything in that was animated. It was just differently animated. And then Disney's like, more expensively animated. And it was cheaper to make because we didn't need to hire one of those pesky writers. What are you talking about? Oh, yeah. So notice that rectangular coordinates was 3 distances. cylindrical coordinates was 2 distances, 1 angle. All right. 3 distance. Cylindrical was 2 distance, 1 angle. So we're going to have a third kind of coordinate. What's it going to consist of? What's the next step in the progression? 3 distance, 0 angle. I'll throw that in there, make it real obvious. Then we go to 2 distance, 1 angle, and we have room for another one. 1 distance, 2 angle. And these are going to be called spherical coordinates. So spherical coordinates will be 1 distance and 2 angle. We only get 1 distance, and we can't just pick R or Z. We have to come up with a whole new distance. The only one that makes a comeback is d theta. There's no more R and no more Z. So this right now is going to have to be a mystery. D theta makes a comeback. So d theta, that's going to be an angle. So we're going to need another factor in our dv to turn the d theta into a distance. The orange one is going to be a distance, so that'll be okay. But the other one, our third variable, since we have 2 angles, we will need another factor to turn d, whatever it's going to be, into existence. It's going to be phi. So in describing 3-dimensional space, we need 3 coordinates. That makes sense. To describe n-dimensional space, you need n coordinates. To describe 3-dimensional space, you need 3 coordinates. At least one of them has to measure some kind of distance. We could measure 3 distances, dx, dy, and dz. We could measure it with 2 distances and an angle, dr, d theta, and dz in cylindrical coordinates. 2 distances, 1 angle. Or we could measure 1 distance and 2 angles. So that would be d rho. We're going to turn our r into a rho, which kind of bugs me because it's still going to represent a length, even though we're using a Greek letter for it. But we'll have a point that's going to be the distance from the origin. Theta is going to be the angle to the points on the floor under it. So that's going to be the same theta. And then phi is going to be the angle measured from the positive z-axis. I know there's no z-axis, but just like we have to measure theta from the positive x-axis, we have to pretend that there's an x-axis there. We've got to pretend that there's a z-axis to measure phi. All right. So let's write a double integral for the volume of a sphere of radius capital R in rectangular coordinates and in polar coordinates. Note that I did not say find the volume of a sphere of radius capital R, because we already know that. The exercise here is not finding the volume of a sphere. The exercise here is taking something that we are familiar with, something to which we know the answer, and seeing if our thinking works in the mechanics of double integrals. Does that make sense? It's not about the answer. Too many people think that about math classes. Oh, it's about getting the right answer. It's not about getting the right answer. It's about thinking your way to the right answer in multiple ways. This is why people, parents, super object to when their kids bring them their homework and they can't do it. It's a blow to their ego because they realize just how bad they are at math. Like, oh, but this is like a third grader and I can't help them. It's like, well, then don't, for one thing, put your ego aside. And don't try to blame someone else. Oh, they didn't teach me this in school. It's like, oh, no. They attempted to teach you this in school. I agree they didn't teach you this, but they attempted to teach you this, but you didn't learn it. That's the story. You know what I mean? It's like, just put your ego aside. It's like, oh, sorry, kid, I can't help you. It's like when my goddaughter was like, oh, Uncle Evan. It was Godfather, but she didn't call me Godfather because we'd seen that movie. I know she was 9, but we showed her some movies. So she couldn't call me Godfather, so she just called me Uncle. So, Uncle Evan, could you help me with basketball? I'm like, oh, no, I cannot. I am very bad at it. I have 0 pointers in that department. I'm not going to be like all mad. Like, oh, I can't believe this kid's trying to play basketball. And I'll come up with reasons that playing basketball is a bad idea. Like, I'm not. I'm just like, oh, no, I can't help you. I will go with you and I will watch you, but don't expect any pointers. And I will go fetch the ball and return it to you, but I cannot explain how basketball works. Take the ball, take the sphere, and put it through the circle. She's like, well, I know that. How do I do that? I don't know. That I cannot help you with. Then you got to bounce it around. She's like, oh, Evan, you're not allowed to use 2 hands. I'm like, oh, why not? Why do we have 2 hands if we're not allowed to use 2 hands to bounce the ball? It's really hard to find with just the 1 hand. You know what I mean? And why do we have to bounce it while we're running anyway? Why can't we just carry it? I mean, I know they don't do it in football because in football, they have the stupid shape of the football. Like a football is like, well, instead of having a ball, let's shape the football all stupid. Oh, yeah, that's good. Make sure it doesn't bounce very good. Yeah, that's great. So did they get this idea from a dog toy, or did they get the idea for the dog toy from the football? Like they were watching a dog play with this irregular shaped piece of wood, and it's like, oh, look at how that thing bounces. Let's make a ball that shape and then invent a game around it. You know what I mean? And I'm talking about American football. If you're watching this from places where football is different. There's only like a few people that are allowed to use their foot on the ball. That's not an original joke. Everybody makes that joke when they want to insult football. Best take on football, George Carlin. Violence punctuated with committee meetings. Oh. Here's another reason that football is stupid. One of your strategies is to not do stuff. Like if you're ahead at the end of the game and you have the ball, one of your strategies is to not run a play. Not attempt to do anything. Just waste time. That's like literally one of the strategies. Don't do anything. Because if we do something and mess it up, then the other guy might get the ball. And then they might score some points. You know what I mean? Because if you're like only ahead by 5 points, oh, we better not do anything. Let's just run out the clock. What a dumb game. Don't do anything. Make sure nothing happens. Stupid football. The worst is how popular college football is. Because why is it so popular to watch a game being played by people that are objectively bad at it? There's like this whole professional league where people like only do this. I realize that when you're in college, you only do that. But that's because the NFL said, instead of having a minor leagues, we're just gonna subcontract this out to the colleges, make them pay for it. Then they all high five each other. And baseball's like, oh damn, why didn't we think of that? And they kind of did, but after you graduate from college in baseball, then you have to go play in the minors anyway. You know what I mean? Anyway. Meanwhile, the NFL, South Park doesn't nail everything, but they nailed this one. It's like, oh, why don't we just use student athletes? People are like, oh, isn't that just slavery? Like, no. They're student athletes. So you're extracting labor from them, yes. And you're not giving them any money, yes. And it's not slavery. Nope, they're student athletes. What are we talking about? Oh, yes. We want to write a double integral for the volume of a sphere of radius r in rectangular coordinates and in polar coordinates. So we know some stuff. In rectangular coordinates, x squared. Oh, we're just going to put this at the origin. I don't want to have to move it. In rectangular coordinates, here's the equation for the volume of a sphere. We're going to have to do a what's x between, a what's y between, and a what's z between. I want to focus on what's z between because z is in common with both rectangular and polar coordinates. We're using the same z-axis in both coordinate systems. So when we go to answer the question about what's z between, we're going to want to solve for z. So z is plus or minus the square root of r squared minus x squared plus y squared. I'll write it in the normal way. So I got the top hemisphere is the plus square root, bottom hemisphere is the minus square root. So our dz integral is going to go from the minus square root to plus square root. That's the bottom to the top. We're also going to have to say what's y between. Then we'll have to say what's x between. Now, when we think about what's y between, we just have to look at the sphere from the top down. From the top view, we're looking at the circle, x squared plus y squared equals r squared. This is going to be the widest part of our sphere. So from our top view, I'm going to write my integral dz dy dx. It has a nice order to it. So I'm going to have to say what's y between. That means solving for y. Y is plus or minus the square roots of r squared minus x squared. When we go for what's x between, that'll be our last integral. That has to be constants. So the x will just go from minus r to plus r. Oh, I didn't have to worry about what's z between because I said write a double integral, not a triple integral. So x will go from minus r to plus r. And the y will go from minus the square roots to plus the square roots. At each point x, y, I'm going to want the distance from the lowest z value to the highest z value. So I'm just going to take the plus square root z, the plus z equals plus square root, and subtract the minus square root. Now, at this point, you should be thinking, dude, isn't that just 2 times the square root? Can't we just take that length and double it? And I'm like, oh, yes, absolutely. That's what happens when you subtract the opposite of something from that thing. You get 2 of that thing. Minus and minus becomes plus. The 2 minus signs Voltron into that first parenthesis. And when it crashes into it, the impact takes that curvy parenthesis and flattens it out. It's surprising to the parenthesis. It's like the 2 minus signs go, and it goes boing, it straightens out, makes a plus sign. That's why 2 minuses make a plus. That's not why 2 minuses make a plus, but it's much more visual. I think of the 2 minuses like all change sign attack, go, and then making a plus sign. And then that's so frightening. This second parenthesis just like faints and fades away. That's the story behind it. If I was able to go back in time and do math as mythology, that's where I would start. One of the things I would do after I introduce negative numbers. Something like, oh, well, why is 2 negatives a positive? Ah, good question. Now, in polar coordinates, I'm just going to be trading my x and y, my z values, and I'm going to have to rewrite my z values. In polar coordinates, I don't have x squared plus y squared equals r squared. In polar coordinates, x squared plus y squared is equal to r squared, little r. I knew this was a mistake, but I went with it anyway. So I'm just going to replace my x squared and my y squared with my little r squared. So in polar coordinates, I don't want to smear this part. So I write kind of weird. This is going to change my dr, my dx dy for a d theta dr. But we can't just use d theta as is. That's not a length. It doesn't give us an area. We have to throw in an extra factor of r. So r double, and also, since we're just doing this whole circle, rather than having to solve for y and then say x between these two values and then y between these two functions, a circle is just two intervals in polar coordinates. So in polar coordinates, actually, I'm going to try to be consistent. At each point, r theta, I still have the top value of z, the positive square root, minus the bottom value of z. It's still going to be two of them, but I'm going to still write it in this separated way because I want to emphasize the top and the bottom part. Also, it's in polar coordinates now. But instead of just writing d theta, that's not enough. That is an angle, not a length. I need another factor of r. And then since a circle in polar coordinates is still two intervals, theta will go from 0 to 2 pi. That's all the way around the circle. And r will go from 0 to capital R. We know eventually we're going to have to get 4/3 pi times capital R cubed. And notice that we're definitely going to want to use the second one. If we have to actually go through the integration, this second one is the one to do. First of all, here's where the pi shows up. It's just going to be something that we plug into a theta. That's better. In this one, there are no pi. Pi shows up because we do like a sine inverse or a cosine inverse of something. And that's because up here, we're going to have to do trigonometric substitution. But down here, that trigonometric substitution has kind of already been done for us. Because here's an r, and there's the r squared. We're going to be able to do a regular substitution. And then just plug in a theta. That's awesome. So if we had to do one of these by hand, the second one is the one that we're going to want to do. Unless we got lots of time and we want to flex on people, then we're going to be like, well, no, I'm going to do trigonometric substitution. But then like 12 hours later, I go 4/3 pi capital R cubed. And meanwhile, these guys are like, oh, yes. And we have also gone and played video games. Any questions? The next thing that we're going to do is this same sphere with this same volume, 4/3 pi capital R cubed, only we're going to write a triple integral. But we're not going to do that today because we are past time. But if you want a head start on what's tomorrow, all right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.